So in chapter 3 we were talking mostly about ions and ionic compounds, and in chapter 4 we start talking about covalent molecules and covalent compounds. So this is a second type of bonding that is very common. So it's chemical bonds that hold atoms together in compounds, and the chemical bonds form as a result of electrons, particularly those on the outer edge of different atoms, interacting. And there's two ways that this can happen. There's what we call sharing of electrons, where two atoms come together and their electrons kind of mingle. And when this happens, we form what's referred to as a covalent bond, and that's what we're going to be talking about in this chapter. And then there's transferring of electrons. Two atoms come together and electrons move from one atom to another. This results in the formation of ions, which become attracted to one another, and then those two ions become stuck together as a result of the formation of an ionic bond, and that's what we talked about in the previous chapter. So this is where we are now. We're going to explain how the sharing of electrons between two or more atoms results in the formation of covalent bonds and what we call molecules. So an important thing to keep in mind is that whatever type of bonding occurs, the atom is hoping to achieve a stable electron configuration similar to a noble gas. So that's summarized in the octet rule that says that when atoms interact with one another, they either share or transfer bonds in order to obtain a noble gas-like electron configuration. And so we saw that with ionic bonding, but we're also going to see this with the covalent bonding as well. So the simplest kind of atom that's out there is a hydrogen atom, and a hydrogen atom has one proton in its nucleus, and then at a great distance from that nucleus it has one electron. And we know from observation that whenever we see hydrogen in nature, it always exists as diatomic molecules. And so what that means is that whenever two hydrogen atoms come together, they get stuck to one another for some reason or another. So in the following few slides, I'm going to explore why that happens. So let's think about two hydrogen atoms that are separated by a large distance. They're basically not interacting with each other. And as I mentioned, every hydrogen atom has one electron and one proton. Now, as these guys come closer together and begin interacting, we have to think about what the interactions would be. So first of all, like charges repel one another. So the electrons on these two atoms are going to repel one another. Similarly, the protons on these two atoms will repel one another, but there will be attraction between the electrons and the protons because they have opposite charge. So if we bring these guys together, they bang into one another such that the region where the electron is placed on one atom overlaps with the region where the electron is placed on the other atom. What do we observe happens? Well, what happens is that the particles organize themselves kind of like this. So we end up with the two electrons spending most of their time sitting exactly halfway between the two protons, which always position themselves at a characteristic distance from one another, and the atoms get stuck. And the reason is because in this arrangement, attractions outweigh repulsions. Sure, the protons do repel one another, but they're at a fairly large distance from one another, and it's only a +1 interacting with a +1. But there's a really big attractive force on each proton inwards towards the two electrons that are in the middle. These two electrons in the middle, they do repel one another, but again, it's only a -1 with a -1. It's not as big as this 2 times interaction, one for each proton, between a proton and two electrons. That's a really big attractive force, and so it outweighs all those repulsions, and these guys end up stuck with one another. Now, the interesting thing here is that every proton, each atom here, represents a hydrogen atom, and now each of the two hydrogen atoms has a share of 2 electrons, just like helium, which is a noble gas. So by getting stuck together, each of the two atoms in the molecule obtains a noble gas-like configuration. As a result, In natural samples of hydrogen, we don't see individual atoms, we see H2 molecules, because when hydrogen atoms come together, they get stuck to one another in pairs. So covalent bonding always occurs between atoms of nonmetals. And when nonmetals come together gets bonded to one another via covalent bonding, they form an uncharged species called a molecule. Remember, we started with neutral atoms, we bring them together, whatever we end up with has to be electrically neutral. Now, it also works out that when groups of atoms come together and get stuck to one another via covalent bonds, they can then go on to lose or gain some electrons and form a species called a polyatomic ion. So within the polyatomic ion, the atoms are actually held together via covalent bonding. But these guys have lost or gained some electrons, so therefore they have a charge. So the atoms that are in these molecules held together via these covalent, also referred to as molecular bonds, they are stuck to one another and they can't be separated by a physical means. You have to use a chemical reaction to separate these atom types. It's important to recognize that different compounds represent different ratios of atom types that are bound together. So for example, water molecules consist of 2 hydrogen atoms bound to 1 oxygen atom, but hydrogen peroxide molecules are composed of 2 hydrogen atoms bound to 2 oxygen atoms in this arrangement here. Now, even though both these guys contain hydrogen and oxygen, because there are different ratios of atom types, they have radically different properties. Water is essential to life, you have to drink it or you die. Hydrogen peroxide in its pure form is very sort of damaging to your skin, and if you was to drink pure hydrogen peroxide, you'd probably die. Okay, so we've mentioned this previously. There are 7 elements on the periodic table, what we call the diatomic 7, that are always found in nature as diatomic covalent molecules. They are hydrogen, which we already previously mentioned, plus you go over element number 7, which is nitrogen, and you draw a 7, and that gives you the remaining 6. It's also important to recognize that under standard state conditions, that means normal conditions of room temperature and 1 atmosphere of pressure, phosphorus exists as molecules of 4 phosphorus atoms, and they're organized in the form of a triangular based pyramid, and sulfur occurs as rings of 8 sulfur atoms. So that's kind of interesting, isn't it? So it ends up being, I'm not going to attempt to draw it, but it's a ring. The molecules are rings of containing 8 sulfur sulfur atoms. Now, under normal conditions, what's often referred to as standard state conditions, so you know what you experience at room temperature, what we find with covalent substances, which is in contrast to ionic compounds, is that they can be either solids, liquids, or gases. So they have a very wide range of melting point and boiling point. If they are solids, their melting point tends to be a little lower than what we see for ionic compounds. So all ionic compounds are solids at room temperature and generally have all have very high melting points. Okay, so that concludes this video introducing the concept of a covalent or molecular compound and also molecular or covalent bonding.